Hello, good evening, all. Uh, can you please confirm if I am audible and my video is visible? Yes, thank you. So, today is the first tutorial for this Quantum Mechanics 1 course. So, before we begin, let's wait for a couple of minutes. Maybe other people are waiting to join. Let's give them a couple of minutes and then we can start. Yes, so there is another session at 7 p.m. today, and that will be taken by another TA, but the content will more or less be the same. The session is just so that if you don't have time at 4 p.m. or something, and if you want to join the later session, then you can join that session. Only the TA will be different, but the problems that we will be discussing today will be similar. Also, I'll be uploading this video on YouTube, and you guys will get the link of both the recorded lecture and the PDF of the problems that we'll be solving today. You will get the link of both. So if you are unable to join because of some reason, so you can watch it later as well. But I would request you to please stay if you can, because the benefit of live sessions is that you can ask questions whenever you want, and if you don't understand any step while solving the problems, you can just get it cleared there and then. Okay, so I guess we can start now. Okay, so this tutorial 1 is mostly based on the material of week 1 that was taught to you guys, and it is mostly the introductory stuff related to quantum mechanics. Okay. Uh, so the problems that we'll be solving will be similar to your assignment 1, not the same problems, but based on same patterns like particle in a box, potential well, harmonic oscillators, right, commutators. So before I start, if anybody wants to ask anything in particular, uh, now is your chance, and then we can directly go to solving some problems. Does anyone has any questions? You can always unmute yourself, ask questions, and you can also feel free to type your messages in the chat box.
Hello, sir.
Hi.
My name is Arya.
Hi, Arya.
I recently registered for this course.
Yes.
Can you tell me the process of how this course happens? Like when you give the assignments and when are the lectures planned? Can you give a brief about it?
Yeah, okay, I can do that. So this course problems to okay. Okay, so this course is starts from January. It has already started. So the content of first week is already uploaded on the website, and every week you'll have 4 to 5 lectures, and based on those lectures you will get an assignment, and you will have like couple of weeks to submit the assignment. And every week you will also have 2 live sessions like this one, where you can uh, ask questions, discuss your problems, or if you don't have any problems, you can just join. And what we will be doing basically is like a tutorial where we will be solving some problems which will be similar to those in your assignments. So this is a 12-week course in total. So you will have 12 weeks. So every week you will have 2 sessions, Saturday 4 and Saturday 7 in the evening. And after that you can register for exam if you want the certificate. Okay, I hope that clears it out. So week 1 is already like today, what we'll be discussing. The problems will be based on the material for week 1.
Okay, so where can I get the lectures for the week one?
How did you get the link? I hope you got the link on the SWAYAM portal from NPTEL website, correct?
Yeah.
Yeah, so on
Okay.
that same portal,
Okay.
you'll get the link for the videos, basically the course material. So if you go to
Okay.
course outline, you'll see different weeks written, week 0, week 1. You can click on week 1, and then you'll get all the materials for week 1.
Okay, sir. And one more doubt.
Yes.
In the week lectures, they will be recorded or the live ones? The week lectures?
The week lectures are recorded.
Okay. Okay. Got it, sir. Thank you.
Yes, no problem. Okay, in the chat, problems 2489 to be discussed. Okay, Miss Jagneet Anand. Okay, so I would just clarify one thing. In these tutorials, because the assignments, though I have not attended. Okay. So in these tutorials, I will not be solving the current assignment that is given to you, right? That kills the purpose of learning, correct? So I think the submission deadline is sometimes in February. So I'm not allowed to solve the problems of your assignments before the deadline is over. If you have doubts regarding some concepts, we can clear them out. But unfortunately, I cannot. Uh, yeah, I cannot solve the assignment problems before the deadline. However, I'll be solving the problems which are very much similar to your assignments. So I guess that will help. Those are the same videos as they are on YouTube. Yes, you are correct, Swapnil. Because this is a rerun. This is not the first time this course is running. This is a rerun. So you can find these videos on YouTube as well. So you can go to NPTEL Quantum Mechanics 1, type the name of the instructor, and then you will basically find the same videos. Essentially, the lectures, they are pre-recorded, they are not live classes. So, and they were uploaded previously on YouTube, so they are available on YouTube. Okay. Any more doubts? Anyone?
One more doubt, sir.
Yes.
Where to submit the assignment and to whom?
Okay, so if you open your SOAM portal, and then you go to basically, okay, let me just show you. Yeah, so if you open your SOAM portal and then you click on the options, there you'll get several things, announcements, course outline, about the course, things like that. If you click on course outline, then basically you will be directed to week 0, week 1, something like that. And there you can click on assignment 1, it's a link, and you will get an assignment which is like MCQ, integer type questions, true and false type questions, which you can just select. So you don't have to send a PDF or scanned version or anything. It's online. So you just have to select the right option, or in some cases, maybe you have to type some integer, and that's it. Then you click submit, so it will be submitted.
Okay, got it. Thank you so much, sir.
Yeah, you're welcome. Is it okay if I haven't completed? So week 0 assignment is generally, because it is week 0, so it is generally for you to kind of get warmed up for the upcoming course. I don't think it is mandatory, but I am not very sure. As far as I know, it's okay if you have not done that, but why not just give it a try? What topics I have to study after starting quantum mechanics 1? Okay, so if you are talking about the syllabus of the quantum mechanics 1, it is mostly based on book by J.J. Sakurai, or you can also follow another book of similar level like Griffiths or Zetley, for example. And quantum mechanics 1 generally, I mean, the syllabus is also given on the course website, so you can check the website, go to different weeks, you'll get the syllabus week wise. So week 1, for example, week 1 is introduction to quantum mechanics and particle in a box problems, or harmonic oscillators problems, something like that. So it is not very advanced. How to strong or basic, I guess solve some problems. If you're finding this course to be difficult, you can start with some modern physics book. There's one very good book by Arthur Beiser, which will give you a very gentle introduction about quantum mechanics. So if you want prerequisites, I think Arthur Beiser is a good book to start. Will we talk about perturbation analysis? Okay, give me a second. Okay, so let me just briefly summarize the syllabus for you. So we will have some simple potentials, right? Particle in a box, harmonic oscillators, bound states. Then we will have one-dimensional bound states. So this will be done in week 2. Okay, wait. So then we'll have vector spaces and operators, uh, function spaces, some postulates of quantum mechanics, and then basically what is the difference between Schrodinger and Heisenberg picture. And then later on we'll look at hydrogen atom, angular momentum, identical particles, and quantum computing. Harmonic oscillator again using ladder operators, and then rotational groups, addition of angular momenta, Clebsch-Gordon coefficients, and finally some tensor operators. So we will not be looking at perturbations in this course. What basic maths are used here? So I think if you are talking about mathematics, if you have done a course in calculus, that's good, and linear algebra. So those two will be required here because we will be talking about vector spaces, and we will also be using differential equations because Schrodinger equation itself is a second order ordinary differential equation. Partial differential equation. I mean, vector calculus, yeah, vector calculus is required because here we, for example, the Hamiltonian that we write in the Schrodinger's equation has that Laplacian in it. Which level mathematics we have to do? I think BSc level mathematics will be good enough. But you must, okay. So as someone has written vector calculus, if you have done a vector calculus course, then I think you are good to go. Okay. And anyway, any mathematics that is used in this course, I think it is explained pretty well in the lectures. And still, if you are unable to understand any of that, that is why we have these live sessions. So do not hesitate at all, because this is your chance to get your doubts cleared. Okay, we have a 2-hour session. We are not in any hurry. We are here for you. That is the sole purpose of these sessions. Okay, the more interactive they are, the more benefit it will give to you. Okay, otherwise we will just solve some problems and hopefully you will be able to learn from them. Yes. Anything else? Which book should we refer to? So if you look at the website, the book that is suggested by the instructor is J.J. Sakurai, Quantum Mechanics. But that is slightly advanced level book. Uh, if you want some alternatives, I would suggest Quantum Mechanics by Griffiths and Quantum Mechanics by Zetterley. So those two are other good books personally which I followed. And Griffiths, for example, is easy to follow. It also has several solved problems. So yeah, that's a very good book. Same goes for Zetterley as well. David Tong lectures, I think, yeah, if those are like every lectures by David Tong, they are very good. His notes are available on his website. If you want to follow David Tong, go ahead. Basically, it depends what level are you interested in, and depending on that, you can select your reference. But official reference for this course is J.J. Sakurai. Okay. Yeah, no problem. Okay. Any more doubts? Example 3 in the tutorial extension. Okay. Yeah, sure, we can do that. So Miss Jagneet Anand is asking about physical significance of probability current density and its significance with regard to wave function. Yeah. Okay. Any more questions? Okay. Okay, so before solving problems, let me just quickly address the concern raised in the chat regarding probability current density. So essentially what probability current density does, okay, let me write here. So probability current density, it is denoted by J generally. Okay, it is a vector. Let's consider only one dimension for now, so it will be a function of your x and t, and how we define it is, this is iota, and then psi star del psi over del x minus psi del psi star over del x. Okay, now there is a thing known as conservation of probability. Okay, let's say our probability p is given by mod psi x comma t square, right? This is the probability density of finding a particle at a point x, right? And then this is the probability current density. So now the physical significance is that if the probability of finding a particle in a specific region decreases over time, right? So over time, if this probability is decreasing, okay, so probability of finding a particle is decreasing somewhere, right? So it doesn't just vanish. So then this continuity equation tells us that it must have kind of flowed out of the region as a probability current j. Okay, so what I am trying to say is, if this is your entire x axis, let's say this is 0, infinite, infinite, okay, and let's say at t is equals to 0, your probability looks like this, and then at later time your probability looks like this. Okay, so if we just consider this position at x is equals to 0, so what is happening is essentially our probability of finding the particle is decreasing, right? It is going down because psi here, okay, let me just write psi of x. Okay, so at x is equals to 0, initially we have some finite probability, and at some later time the probability has decreased. Now what this probability current density means, that this probability kind of flows to some other x, it kind of redistributes in space. Okay, that's why we are calling it current. Okay, it is similar to your conservation of charge. So this current term is coming from your this charge equation, right? Because your charge is also conserved. Similarly, here our probability is conserved, and that's why we are using the term probability current in analogy with the charge and the current that we study in electrodynamics. So similar to flow of current, like your charge flows from some region to other region when you apply, let's say, a voltage. Similarly, with time, your probability is flowing like electrons, okay, such that your total probability is conserved, right? we know that total probability always has to be 1, and if the probability has decreased here, so it should have increased at some other points, correct, so that the sum of the total probability is 1. Okay, is that clear? Okay, good. Any other questions before solving the problems?
Uh,
Yes,
I'm Jagneet.
hi ma'am.
Hi. Just a query about if I have a infinite potential well,
Yeah,
so it will have the wave function zero at the boundaries,
yes,
and then it in between it is a sine function.
yes,
It will have some ground level E naught energy eigenvalue, right? Now, if I go from infinite potential well, if I move towards a finite potential well,
yeah,
so the wave function will decay finitely into the side regions.
yes,
So that means the ground level energy
mm-hmm.
should reduce if I keep all other factors the same, like the width of the potential well is the same, but the height of the potential well is reduced from infinity to. So that means the value of the energy will reduce. Am I
Okay,
okay? Right?
mm-hmm.
I just wanted to apply it to the case of, like I just checked, asked you about perturbation.
Yeah,
That means if in a in the case of a real device, for example, if I have a gallium arsenide crystal
yes,
which has a conduction band and a valence band, and if I apply an external voltage,
mm-hmm.
so does that mean if it is a potential well,
Yeah,
okay, gallium arsenide surrounded by the higher energy band gap material, so gallium arsenide will be a potential well.
yeah,
So now if I apply an external voltage,
mm-hmm.
so that means in the gallium arsenide region, the height will change, the height of the potential well will change.
Yes,
So will that mean that if the electron is now making a transition to the valence band from various eigenvalues of the from the conduction band to the valence band,
yeah.
so the frequency will change if I change the voltage that I have applied? I'm just curious. Am I
Frequency
understanding
of
it correctly?
frequency of
The photon that is emitted when an electron makes a downward transition
okay.
from the conduction band to the valence band,
Mm-hmm.
will that frequency, I mean, will the color of the photon emitted change if I change the voltage applied across this particular LED or this particular device, heterostructure device?
I don't think so. The reason is
Hmm.
because we are when we are talking about bands,
Uh-huh.
and what we are essentially doing is when we are applying a voltage,
Hmm.
so basically we are providing some extra energy to the electrons,
Hmm.
maybe some positive energy or negative energy depending
Mm-hmm.
upon the bias of the voltage that we are applying.
Okay.
But the transition that happens
Mm-hmm.
is from conduction band to valence band, and that the photon that is emitted will be decided by your delta E, correct?
Hmm. Yeah.
Which is in this case our band gap, correct?
Yeah, but the center region
Mm-hmm.
is very thin.
Okay.
So, like gallium arsenide, which is
Yeah.
it is so thin that it can be treated as a potential well, a finite potential well problem.
Mm-hmm.
So that means the levels in the conduction band, it will have
Okay. Just I think.
quantized
Okay. Let
levels.
me let me just say one more thing. So
Yeah.
we know that when we have core levels, so they are discrete energy levels, right? For example, in an hydrogen atom, we study that we have discrete levels. But when we bring these atoms close together, what happens is these levels overlap and what we get is a band. Now when we have a band, we no more have discrete levels. That's why it is a band. Correct? So all the possible states are allowed inside the band. It is a continuum. It is no more a discrete energy spectrum. Are you following?
Yeah, but we have quantum well LEDs. I mean,
Mm-hmm.
if the thickness is very small, so that is like I can compare it with a potential well problem. The potential well problem, we have discrete levels.
Yeah, but what I'm saying is in bands you don't have discrete levels. So okay, so let me
Okay.
just draw. So you'll have, like, for example, this is your nucleus. You'll have discrete levels, right? Like these are the energy levels, but later on when they grow bigger, so they'll form a band. Correct?
Yeah, yeah.
Yeah. So when you have like these kind of levels, and later on, so these are core levels, and higher you have bands. So let's say this is your valence band, and this is your conduction band, and this is your band gap. So here basically what I'm saying is it's no more, you cannot think of these bands as these levels here. They are not discrete. They are a continuum. And depending upon your Fermi, you will know to what point are they occupied. Okay, let's say your system is metallic, you have done some doping. Okay, so your Fermi is here. So electrons are filled all the way up to here. Okay, and then why is it a metal? Because all this region is empty, right? So it is not a completely filled band. So electrons can easily go to this region and they'll conduct. Now when they come back, because it is a continuum, so you will not get a single frequency of light. That is what I was trying to say. Now imagine your Fermi is not here but here. So your conduction band is completely filled and your valence band, sorry, your conduction band is completely empty and your valence band is completely filled. Now again you have all these levels, right? You don't know from what energy to what energy they are going, so you will have not just one frequency but a continuum of frequency. However, you have this band gap, right, Vg, and this will kind of decide your most pronounced frequency if you wish.
Okay.
Okay.
Okay, thank you.
Okay, any other question? No. Okay, if not, let's let's read our first problem for the day. And the problem is the energy eigenvalue and the corresponding eigenfunction for a particle of mass m in a one-dimensional potential v of x are is equals to 0. Psi of x is this. So what we are given? We are given two things. Firstly, we are told that E is 0 and we are given our wave function to be some constant a over x squared plus a squared. Okay, and once again, yeah, right. So this is our wave function, and what we are asked is the form of potential Vx. So we are asked that what will be the form of potential Vx. Okay. So we know our Schrodinger equation. Schrodinger equation is H psi is E psi, right? This is our Hamiltonian operator, which has two parts. So we can write it as kinetic energy plus potential energy times psi is E psi. Okay, and we know kinetic energy is just p squared over 2m. Now this is our momentum operator, and then plus v psi is E psi. Okay, and now we are given that our energy is 0. So basically our right hand side goes to 0, and we are asked about v, that what is the form of our potential v of x. Okay, and this is the wave function that we have to use. So okay, let's start. So again we can write this p squared over 2m. We know what is our momentum operator, we know kinetic energy, so let's write. So our equation will become minus h cut squared over 2m d2 psi over dx squared plus vx psi, and our right hand side is simply 0. Okay, and this is our wave function. So let's take its derivative, because we will need to substitute the derivative here. So our d psi by dx will be d by dx a over x squared plus a squared so this will be simply minus a over x squared plus a squared whole thing squared, and then 2x. Okay, so what I have done is I have applied chain rule. So we know that derivative of 1 over t is minus 1 over t squared, here minus 1 over this thing squared, and then taken the derivative of things inside. So derivative of x square plus a square will be simply 2x. Okay, now let's solve for its second derivative. So this will become minus 2a over x squared plus a squared cube into 2x this will be plus and then minus 2a x squared plus a squared whole squared. Okay, yeah. So if we solve this, what we should get is we will have 2a over x squared plus a squared cube common outside, and then this will be multiplied by 3x squared minus a squared. Okay, so then writing it properly, we will have 2a 3x squared minus a square over x square plus a square cubed. All right. So this is our second derivative, and then let's say this is our equation 1. We can substitute this back in equation 1. So what we will get is, we will get minus h square over 2m, and then this minus h square okay, and then we have vx times psi, and we know our psi is simply a over x square plus a square, so v of x times and this is 0. Fine. So then basically what we will get, okay, these two will cancel and we'll be left with h squared over 3x squared minus a squared over m and x squared plus a squared squared. Okay, this thing. Okay, let's quickly check the options. Yeah, so option A, right? If you look here, this is exactly matching with what we have. Okay, so answer is A. So just to quickly go over the problem again, what we were given our wave function, okay, and we were told that the energy of the particle is 0. So we had to find the form of the potential. What we do is simply solve the Schrodinger's equation, h psi e psi, and for that we have to take double derivative of psi. So basically psi. Any doubts in this? Okay, good. So then we can go to our second problem, where we have that consider a photon that scatters from an electron at rest. If the photon scatters at an angle 60 degree with a wavelength lambda prime, that is twice its incident wavelength lambda, then the angle at which the electron recoils will be dash degrees. So we have to give an integer answer. Okay, so let's say we have an electron and it is at rest, and then we have a photon which is coming towards the electron and its incident wavelength is lambda. and then what happens, so you can say that psi function no actually, see, if you, okay, it is not, we cannot say it is the distance function. And why we cannot say so is, like, here I'll just explain quickly. So your distance, we generally write x, and it has units of length, right, L, correct? But what is the unit of wave function? So we have wave function, let's say we are just talking about one dimension, psi of x. So does anyone know what are the units of a one dimensional wave function? Okay, uh, forget that, we know the normalization condition, right? That psi square dx, correct, psi square dx is 1. Now this has dimensions of length, so our psi must have dimensions of 1 over under root L, such that when we square that and multiply by L, we get a unitless probability, right? Because probability doesn't have any units, so it has units of 1 by under root L, which means that we cannot think of a wave function like distance. Both of them are separate things, okay? If you want, okay, so the only physical significance or the physical way of thinking about a wave function is in terms of probability, right? So basically, if you have, let's say this is your one dimensional space x, okay, let's say you consider some point x naught, and then what we do is we take a very small region like we do in calculus of thickness dx, okay, and then the wave function at x naught, so psi at x naught, basically okay, mod of psi square at x naught gives you the probability p of finding, this is like the probability density, okay. So the probability that you have that your particle is in this region, okay, that probability is given by your psi square. So your wave function, okay, it is a function of x, so at any x your wave function is telling indirectly what is the probability that your particle is in that position. And then your wave function also contains a lot of other information. For example, you can always plug in your wave function in a Schrodinger equation, and then you will get energy eigenvalues. So what you are getting is different possible energies corresponding to that wave function, okay, and it is nothing to do with distance, so don't confuse the two, they are completely different things. Okay, so yeah, back to our problem. So let's so our problem was that a photon scatters from an electron at rest. So our electron is at rest, and then our photon scatters at an angle 60 degree. So our scattered photon goes here at an angle of 60 degree with wavelength lambda prime, which is equals to 2 lambda. So our wavelength has increased, correct? Our wavelength has increased, which means our energy has decreased, correct? Both because they are inversely proportional. and the remaining energy will be taken up by the electron, and then the electron will recoil at some angle, and we have to tell that what is the angle at which the electron recoils. So if you have followed the lectures, essentially what we do here is we do conservation of energy, right, and also conservation of momentum. Okay, so our total energy is conserved and our total momentum is conserved. Now using both these conservation laws, does anyone know what is this, what is the name of this phenomena when your photon scatters with an electron and it is emitted with a different wavelength? Compton effect, correct. So this is a problem based on Compton effect. Yeah, exactly. And for Compton effect, we can, sir, may I know from where these questions are taken? So these questions are taken from the assignments of the courses that was run in 2025. So this same course, but last year's assignment. Okay. Okay. So we have Compton. So this is called Compton shift, right? We know that delta lambda, which will be lambda prime minus lambda, it is given by h over MEC 1 minus cos theta. And the recoil angle is given by, so recoil angle is phi, okay, and we have the equation tan phi is sin phi over lambda prime by lambda minus, oh sorry, this is sin theta minus cos theta. So phi is the scattering angle of the electron, whereas theta is the scattering angle of the photon. Okay, so theta we are given as 60 degrees. Okay, so now using this equation, we are given theta is 60, so our tan phi will become, so sin 60 is under root 3 by 2, and then lambda prime is 2 times lambda, so this is simply 2, and cos 60 is 1 by 2. Okay, so we can simplify this to under root 3 over 4 minus 3, 4 minus 1. So our tan phi is under root 3 over 3 or 1 by root 3. So our phi is then tan inverse 1 by root 3, and tan inverse 1 by root 3 is 30 degrees. Okay, so pretty simple problem if you know the formula for electron recoil. Okay, so just to quickly go over the problem again, it is based on Compton scattering. Our photon hits an electron gives some energy. Yeah, 30 degrees is correct. CS Dhinakar. So it gives some energy to the electron. Our electron recoils, and the new photon that is emitted has lower energy, therefore greater wavelength, and it is emitted at some angle 60 degree. So to conserve energy, we know, okay, the remaining energy goes to electron, but we also have to conserve the momentum, right? We also have to conserve the momentum. Therefore the electron will also be scattered at some angle. So electron will be scattered at some angle phi, such that our uh, total momentum is also conserved. Okay. Yeah. So should we proceed? Okay, any doubts before solving the next one? Okay, let's look at it. So what we have? We have a 1D problem. So we have particle in a one-dimensional box, and we are told that its ground state energy is given by E naught. Okay, ground state energy E naught, and then out of these 4 energies, 2 E naught, 4 E naught, 6 E naught, and 9 E naught, we are asked that the allowed energies of such a particle are. B and D. Yeah, B and D. So if you remember the energy of a particle in a one-dimensional box, we know that En is n squared pi squared h cut squared over 2m l squared. And for ground state, our n is 1. So ground state means n is 1. So our E naught will be pi squared h cut squared over 2 ml squared. Then we can write our energy En to be, in terms of E naught, we can write it simply as n squared times E naught. Okay. So basically this entire thing, this is E naught. Good. So then we say, okay, when n is 2, so our energy will be 4 E naught. When n is 3, our energy will be 9 E naught, right? So squares, and then the next one will be 16 E naught, and then 25 E naught, and so on. So the coefficient of E naught has to be a perfect square, and if we look at our options, option B, okay, option B and option D, because here we have 4 E naught and there we have 9 E naught. So this was a multiple select question, and we have 2 correct options. Okay, I hope this is clear. Yeah. Okay. So this was a 1D box. Now next problem is a 2D box. So consider a particle in a 2-dimensional box. Again, the ground state energy is E naught. So what the question is, then the energy E is equals to 13 E naught is 2-fold degenerate. True or false? Okay. So our ground state energy is E naught, and then the question asks whether the energy E, which is 13 times the ground state energy E naught, is 2-fold degenerate. Okay, true. Yeah, true. Okay, so how do you write the energy in a, like, for a, we just wrote for a 1D box. For a 2D box, the energy is written as nx squared plus ny squared, and again the same coefficient pi squared h cut squared over to m l squared. True, yeah. So okay, now if you remember in the last problem, what we had done was we had put n as 1 for ground state, correct? So that was our ground state energy. Now I want to ask you one question, that what will be our ground state energy here? Can we put 0 here and 1 here? Yeah, we cannot do that. So for ground state, we have to put nx also 1 and ny also 1. And therefore our E naught will be 2 times pi squared h cut squared over to ml squared. Okay. So this is what we have. Now energy E, which is 13 times E naught. So our E then will be 13 times this. So basically nx squared plus ny squared and then we can, if we write in terms of E naught, so this thing is simply E naught by 2, right? So now we have this equation and we are given that our energy is 13 E naught. Okay, so this is equals to 13 E naught, and we then cancel out E naught and this becomes 26. Okay, essentially what we have now is this equation. So we have nx squared plus ny squared is 26, and we know that these n can only be integers, so they can only have values 1, 2, 3 and so on. And now how many ways are there to satisfy this equation? So there are clearly 2 ways. One is, so the first way is you put nx as 1 and ny as 5. So your 1 squared plus 5 squared will be 1 plus 25, which is 26. And the second way is that your nx is 5 and your ny is 1. Okay, so we have now 2 possible states. So our wave function can decide in 2 possible states. Therefore this energy state, which is equivalent to 13 E naught, this has 2-fold degeneracy. Got it?
Excuse me, can
Yes.
you just elaborate why it is E naught by 2? I think I missed that.
Okay, so I'm just it's just hmm. So what we have here, okay. So I think up till here it's fine, right? Right?
Yeah.
Yeah, and then if you look if you look at E naught, we put nx as 1, ny as 1. So our E naught is then 2 times this number, pi squared h squared square over 2 ml squared. So what I am doing is, I can bring this 2 down here, right? I can write E naught by 2.
Okay, okay, I got it.
Got it now?
Just a clarification, if it is a three-dimensional, then it will be 3 here. So
Yes,
the
this
ground
dimension
state
will
will
be
be
3.
3 here.
Yeah, yeah.
That's it. Okay,
Correct,
so
correct.
that is where it is differing from one-dimensional.
Exactly, exactly.
Okay, okay.
So what this means is, basically we cannot take this coefficient to be E naught. It will be
Yeah. Yeah.
it will be multiplied by a factor of half,
Mm-hmm.
and there 1
Okay.
by 3 and so on.
Okay, thank you.
Yeah. Okay. So now let's go to a 3-dimensional box. So we have done a problem on 1D box, 2D box, and next we have a 3D box. So we are told that second energy level, okay, second energy level in a cubical box is given by E is equal to 6 Eg, where Eg is the ground state energy. Then the immediate third energy level will be dash fold degenerate. Okay, similar problem, but for a particle in a 3D box. So here again we will have, instead of nx and ny, we'll also have one nz. And then the same factor of pi squared h cut squared over 2ml squared. So our Eg will be simply 3 times this, right? 1 1 1. So 3 pi squared h cut squared over 2ml squared. And as we did last time, we can write our energy in terms of Eg, in terms of Eg. So this will be Eg by 3. Clear? And now we are given that our energy, this E, this is equal to 6 Eg. Okay, so E is 6 Eg. So if we compare these two equations, what we will get is that this nx squared plus ny squared plus nz squared, this thing will be equal to 18. Okay, and this is the second energy level of a particle in a box. Okay, so this is the second energy level. Okay, so and we know that our second energy level, so for second energy level we have nx is 2 and ny is 1 and nz is 1. Okay, so for the threefold, yeah, correct, threefold degenerate. So for the immediate next level, as it is written here, then the immediate third energy level will be, so for the immediate third level we will have nx is 2, ny is 2, and then nz as 1. This will be, so this is one way of getting to the third level. This is one way. Okay, so I can simply write it as 2 to 1, for example. What we can also have is 2 1 2, and finally what we can have is 1 2 2. Okay, so once our nz is 1 here, next time our ny is 1, so ny is 1, and finally our nx is 1. So these are three possible ways, which corresponds to threefold degeneracy.
One query.
Yeah.
It is n square, nx square plus ny square plus nz square is 18.
Yeah.
So if I take n2, nx2, ny1, and nz1,
Yes.
then
This
it,
equation is not satisfied, right?
yeah, yeah.
So either I can think of two things, that maybe there is a some error in the problem, right? Some typo or something, that this should not be 6 times EG. It should be 1 1 4 pairs. Yes, correct. So if you take 4 1 1, if you take 4 1 1, then it is satisfied.
Yeah,
Yeah, but that is not the second energy level,
yeah, that is not.
right? So either the typo is in the
Okay.
here, writing in the second energy level, or in here, writing 6 times EG.
So 411 would be which energy level? It is not ground, it is not one. Is it fourth energy level?
No. Okay.
Then
So we'll have to calculate the energy of all the levels before.
okay.
We can do that. It won't take much time. So your 111 will give you 3, right? 1 squared plus 1 squared plus 1 squared. And your next will be your 2 squared plus 1 squared plus 1 squared, which will give you 6, right? It will give you 6. And then your next one, where you get this thing, will give you 9. Yeah, this will give you 12, and then your 3 squared plus 1 squared plus 1 squared is giving you 11. So this energy level is basically here, and then 3 squared plus 2 squared plus 1 squared is giving you 9, 10, 14. Okay, and 3 squared plus 2 squared plus 2 squared, so this is 17, and then comes your 411, which will give you 18. Okay, and then again you will have 3 squared plus 3 squared plus 1 squared, which will give you 19. So this is the, okay, let's say this is your ground state. So this is your second, third, fourth, fifth, sixth, seventh, eighth. Then this is your 8th energy state.
Okay, thank you.
Yeah. Okay. Yeah, so the next problem we have is regarding our commutator brackets. And the question asks, the non-zero commutator brackets are. So B. What about A? Okay, let's go step by step. So A is x comma px, right? So our x is the position operator and px is the momentum operator. Does our position and momentum operator commute with each other? Yes or no? Um, yeah, correct. B is the zero commutator. So this is, we know that this is iota times h naught, which means this is not equals to 0. So this is definitely a non-zero commutator. And then we have x comma py. Notice that this is the momentum in the y direction, py, and this is the x position, and both of them, they do commute actually. So this is 0, so b is 0. What about c? X square comma px. Now what we can do is we can write it like this using the product rule, x comma px right. And now we know that this is iota h, this is iota h, so this simply becomes 2 iota h times x. Again, this is not 0. Okay. Yeah. And finally we have x comma px squared. Again, using same rule, we can write px x comma px plus x comma px commutator times px, 2 iota h cut times px, which is again non-zero. So our correct answer is A, C and D. So we have 3 correct answers. Okay, is this clear? Okay, if yes, then let's go to the next problem. So we are given that at time t is equals to 0, we are given time t is equals to 0, and we are given the wave function psi of x. So let's draw our x-axis. Let's say this point is minus a, this point is 0, and this point is plus a. Okay, so inside of this region, our probability, our wave function psi is a times a squared minus x squared, and outside of this region our wave function is 0, both here and here. And then they are saying where both capital A and small a are positive real constants, and what they are asking is the normalization constant A is in terms of small a. So we have to find out this A. So what is the normalization condition? Okay, to normalize a wave function, we set the following integral, which is minus infinity to plus infinity mod of psi x square dx is 1, right? Because the total probability of finding a particle in all space is 1. Now what we can do is we can break down this integral in three regions. So from minus infinity to minus a, then from minus a to plus a, and finally from a to infinity. And we know that the wave function in these two regions, here and here, the wave function is 0. So this term goes to 0 and this term goes to 0. So then what we have is this integral from minus a to a. What is the value of wave function psi here? It is a times a squared minus x squared. Okay, so this entire thing squared times dx is 1. Good. So let's take out this a. So what we will have is, we will have a squared outside, integral minus a to a, and this will become a to the 4th minus 2a squared x squared plus x to the 4 times dx is equals to 1. So now we have to just solve this integral. Okay, so a square is outside, and then this first term is a constant, so a to the 4, and just integral dx will give us x, right? And for second one we will have 2a square as constant, integral of x square will give us x cube over 3, and for final term we will have x to the power 5 over 5, and then we have limits going from minus a to plus a. And this entire thing is equals to 1. So let's put the limits. A squared, so this will become a to the 5, and minus 2 over 3 a to the 5 plus a to the 5 over 5, and then minus, so this will become minus a to the 5, and then this will become plus 2 a to the 5 by 3, and then this will become minus a to the 5 by 5. So essentially we can take out this minus sign outside and it is the same thing. So our a squared, and then we can take a to the 5 outside and a factor of 2 outside, and inside we will just have 1 minus 2 by 3 plus 1 by 5. Okay, so if we take LCM, this is just 15 minus 10 plus 3 over 15, and this is 5, so this is 8, so this is 16 by 15, right? So our a square times a to the 5 into 16 over 15 is 1. So finally this is our a. Okay, just some lengthy calculations and nothing more. So does it match any option? Yeah. So option C, which is under root 15 over 16 a to the 5. Okay. Any doubts in this one?
Just one query.
Yes.
The question is given the wave function at t is equal to 0.
Yeah.
Yeah. Can you please tell how will it evolve with time? If I
Okay.
want to see the evolution with time,
Yeah.
how will I proceed?
So do you know what is the time dependent Schrodinger's equation?
It just get multiplied with e to the power minus iota by h bar into et.
Correct. So
So is it just this?
yeah, yeah. So then what we have to do is essentially find out the energy eigenvalues of this. Correct?
Yeah.
Yeah. So once you have the energy eigenvalues of this wave function, then you have the factor, I mean the value of E that you need to put in the factor e to the power iota et by h cut.
Okay.
Correct? So if you want to know how it evolves with time, then we have to first solve the time independent Schrodinger equation to find out the energy eigenvalues.
Okay. First, solve the time independent. Okay,
Yeah.
this particular equation, and
Yes.
find out the okay. Okay,
Yes.
I'll try that. I will try that, and otherwise, I will put it in the.
Problem is, okay, why it won't be possible here is like you will have to assume some potential. Okay, we are not. So this question, it does not say anything about the system.
Okay.
Okay, so it just says you have this wave function. We don't know the form
Okay.
of the potential or any energy. So for example, if you, this equation looks familiar, right? Was this in question 1? No, little bit different. So here, for example, we were given that, okay, E is equals to 0 is one energy eigenfunction. And then we were able to find out the potential V. Now in this problem, we have two unknowns. Okay, we don't know
Okay,
energy
if I
and we
take
don't know
v
the
is equal to
potential.
0, we
Sorry.
start with v is equal to 0.
Yeah, we can start with V is equals to 0.
Okay. Okay, let me try. Maybe I'll
Okay,
ask the next time. Yeah,
sure.
thank you.
Okay, any other question? If not, okay, then let's go to the next one. Right. So again, now this time it is given that the system is a two-dimensional square box of length L and time is t is equals to 0. So our wave function is defined at t is equals to 0. This is our wave function at t is equals to 0. And then what they are saying is what what will be this wave function at any time t. Now this time, unlike the previous question, we know what is our system. So we know what is our potential. So outside the two-dimensional square box, potential is 0. And inside the box, outside the potential is infinite. And inside the potential is 0. Okay. And this is the form of the wave function which is given to us. Now, okay, if you, okay, let's write the wave function first. So we are given that psi xy at t is equals to 0. This is 1 over root 5 phi 1 comma 2, okay, which is a function of x comma y plus 2 by under root 5 phi 2 comma 1 x comma y. So what does this mean? Okay, so if you see our total wave function, okay, so this is our total wave function. It is written in terms of two other wave functions. Okay, so this is our total wave function psi. So psi, so basically it is written as c1 times phi 1 plus c2 times phi 2, and this is called superposition. Correct? So we have here, we have, this is our phi 1, so this is the first wave function. This is phi 2, this is our second wave function, and our total wave function is written as superposition of both these wave functions. Okay, so you what is phi 1 2? Because it's the particle is in a two-dimensional box, so for phi 1 2, our energy corresponding to phi 1 2, let's write it as E 1 2, that will be 1 squared plus 2 squared times pi squared h cut squared over 2 ml squared. So this will be 5 pi squared h cut squared over 2 ml squared. Is this correct? So basically phi 1 2, so this 1 2 is essentially giving us information about nx and ny. Okay, so phi 1 2 means that our nx is 1 and ny is 2. Similarly, E 2 1 will mean that our nx is 2 and ny is 1. So energy in both the cases is actually the same, and we have just solved few problems where we were talking about degeneracy. So this is a degenerate state. Yeah, D is the correct answer. So so this is a degenerate state, right? Because both these states, phi 1 2 and phi 2 1, they have same energy, and this is a degenerate state. Okay, so instead of writing E 1 2 E 2 1, let's just write that our energy E, which is same in both the cases, E 1 2 or E 2 1, let's just say that our E is 5 by 2 pi squared h cut squared over ml squared. Okay, and now we know that psi at any time t is just psi at time t is equals to 0 multiplied by the factor e to the power minus iota e t by h cut. Okay, so then we can write our psi as okay, so this was our wave function at 0 which was 1 by root 5 and phi 1 comma 2 x comma y plus 2 by root 5 phi 2 comma 1 x comma y, and then multiply this entire thing by this factor e to the power, okay, How about I make this little small? Okay, and then this will be multiplied by e to the power minus iota 5 pi squared h cut t by 2 ml squared. Okay, so basically the same wave function and multiplied by this factor e to the power iota 5 pi squared h cut t by 2 ml squared. So if you look at the options, as someone pointed out in the chat, option D, and as someone also pointed out in the chat, there is a typo. Instead of h cut squared, it will be simply h cut, because one h cut gets cancelled out. So unlike the previous problem where we did not have information about the system, like for example we could not find out this energy, right? We were unable to find out what this energy will be in the previous problem, but in this case we can do that because we know that our system is a simple two-dimensional box. So we can write our energy as this, and then it is very straightforward that we just multiply it with this factor. Okay, I hope it is clear now. Okay, good. So we only have a couple more questions to go. Let's have a look at them. And these are very small questions, should not take much time. Okay, so we have uncertainty in momentum. Okay, so this is our normalized wave function. Okay, this is our wave function, psi of x, a times, and then its exponential iota ax minus iota bt. So we have x and we also have t, and capital A, small a, and small b are constants. Okay, the uncertainty in its momentum is, so we are asked about, uncertainty in momentum. So what is the uncertainty in momentum? So first of all, let's write our momentum operator. We know that our momentum operator is this one. And then let's see what happens when we apply it on our wave function. So let's do p of psi. Okay, so our p of psi will be minus iota h cut, and then take the x derivative of psi of x. So what will be the x derivative of psi of x? If I just take the derivative here, so del by del x a, and then here we have iota ax minus iota b times t. Right, so this will be simply equals to iota a, and then the same wave function again. Yeah, so this is just psi, so iota a times psi. So what we get here So what we get here, we get that our p of psi, so this iota squared is -1 and this becomes +1. So it's just a times h cut psi. Now if we look at this equation, what we notice is that this psi is an eigenfunction of our momentum operator, correct? Because when we operate p on psi, we get back the same psi multiplied by a constant, and this constant is our momentum eigenvalue. Okay. so our particle is in a pure momentum state. Okay, this is our pure momentum eigenstate. We have well defined value of p as a times h cut. This value is well defined, so we do not have any uncertainty in momentum, therefore delta p is 0. Okay, so correct answer is option C. Yeah. So generally when we talk about some realistic wave functions, like a wave function for a particle in a box or harmonic oscillator, so those wave functions are typically not like you do not have the momentum operator acting on them giving you the same wave function. Okay, so that's why there is some uncertainty in momentum. But this wave function that is given to us, there is no mention about the system it comes from, and this wave function is designed in such a way that when you apply the momentum operator on this wave function, you get an eigenvalue and the same wave function, essentially making it an eigenfunction of the momentum operator. And when you have an eigenfunction of momentum operator or any operator, then the uncertainty in that operator is 0. So here it was momentum, so uncertainty in momentum is 0. Okay, so last problem, and it is a double slit experiment. We have two slits, 1 and 2. Okay, let's say these are the two slits. So this is slit 1 and this is slit 2, and they are emitting waves. So this is emitting psi 1 and this is emitting psi 2, r comma t, r comma t. So the question asks, if the intensity produced on the screen, if this is your screen, the intensity I is given as mod of psi 1 squared plus mod of psi 2 squared. Is this true or is this false? Okay.
The wave functions add, right, for intensity, na? For interference.
Yeah, correct. So is it true or false?
The statement that we have written is false.
This is false, right? What should be the correct one?
It should be psi is equal to psi 1 plus psi 2.
And then yeah, so
And then proceed accordingly.
yeah, correct. So this will give us this thing, correct?
Yeah.
Yeah. So this is the correct one and this is the wrong one. So this statement is false. Okay. So basically what what we are saying is that even though we have some particles, okay, which are given by these wave functions, let's say we have electrons, uh, psi 1 is coming from slit 1 and psi 2 is coming from slit 2. If we just consider a classical picture, we will add the electrons separately, right? We'll say, okay, so psi mod psi 1 square is the electrons coming from slit 1, and mod psi 2 square is the number of electrons coming from slit 2, right? So then our total intensity will be mod psi 1 square plus mod psi 2 square. If you think in terms of classical mechanics, then this seems feasible. But because we know that electrons have a quantum nature to them, we cannot just treat them as classical particles. In fact, what we see experimentally is that electrons behave in the same way as light. So electrons will also give us an interference patterns just like light. So as C.S. Thinakar mentioned in the chat, that there is this superposition principle of interference. So we study the superposition principle of interference when we study optics and when we study about light. Here, although we have particles, but we know that those particles have the wave nature associated with them. And when we perform such an experiment, which basically detects the wave nature of a particle, the interference essentially tells you if your system behaves like a particle or a wave, even though we have electrons or some other quantum particles going through these slits, we actually do get an interference pattern. So thinking classically, you might think, okay, this is the correct statement, this is the correct way to find out the intensity, but it is actually incorrect, both given by quantum mechanics and also as observed in experiments. Okay, so yeah, okay, so just one quick note. If you are interested in this double slit experiment, there is a beautiful section in lectures by Feynman. So you can refer to Feynman lectures for this double slit experiment of electrons, where he discusses in detail what happens when you put a detector in front of one slit or detector in front of the second slit, and how this basically your interference pattern changes just by detection. So essentially what he is trying to say is, if you detect a particle, essentially if you measure the particle, it collapses in one of its state, and then you no more will get the interference pattern. Then so basically a particle is a wave unless it is detected. Once you measure its state, it just collapses and it starts behaving like a particle. Yeah, I hope that will motivate you to actually go through the Feynman lectures. It is very beautifully explained there. I think in 3 to 4 pages, and I promise you it will be a good read for your weekend. So before we end today's session, do you have any questions? Sir, can you please switch to question 1? I haven't wrote for question. Yeah, sure, I can go to question 1. So this is the previous year assignment. Okay, this is the previous year assignment, and what I will do is I'll make a PDF of this entire thing that we discussed today, and the link for that PDF will be provided to you shortly. So if you want to practice these questions, then you can go through them. Unfortunately, I don't have more previous year assignments. This is the only one that I have. Okay, I hope today's session was helpful in some way, and I hope to see you guys in the next session next Saturday, same time. Okay, if you have any questions or anything that you want to discuss, you can stay back, otherwise you can leave, and then we'll meet next week. Okay, thank you so much for the comments. Anyway, this video will be uploaded to YouTube if you want to again have a look at the problems that we solved, and that link will also be provided to you. Moreover, you can always ask your doubts in forums, and either the instructor or the TAs will happily answer your queries in the forum section. Okay, if you don't have anything else to ask, then have a good evening ahead, and we'll meet next Saturday. Thank you.